So what is the log ratio of ST to S0? Well, it's a sum of the log of these normally distributed returns. And so one might imagine that if we were assuming normality, the question then would become, what happens to this summation when h goes to 0? How do we deal with the summation of logs of 1 plus returns, and those returns, the r's, are normally distributed? Well, we're going to do a little bit of math that will motivate the result we saw earlier. Since h is going to be going to 0, we're going to use an approximation. You may recall that in earlier work we used a Taylor series approximation for e to the x, that when x was small, we could approximate it by 1 plus x. And there's an error term, of course, and the error term looks like an x squared. I'll call it big O of x squared. That means that the order of magnitude of the error looks like x squared when x goes to 0. Similarly, for a logarithm, the log of 1 plus x can also be approximated by a Taylor series, the first term of which is x, the second term of which is actually a negative half x squared. We'll think about that in just a moment. But for the time being, this is a pretty good approximation for log of 1 plus x when x is small. So let's go back to that summation. If we ignore the error for the moment, the sum of this log is pretty much the sum of the returns, because each logarithm is approximately the return.
Start that sentence again, and
Okay, so I'll start that sentence again now. So if we're willing to ignore the error term for just a moment, the sum of the returns is a sum of logarithms. And we see here that using that approximation, the sum of the logarithms of the 1 plus return is the same as the sum of the returns themselves. There is an error term which looks like the sum of the returns squared, and we'll be back to that in a moment. Hence, if I look at the log of the ratio of ST to S0, it's basically a sum of these returns plus an error. Now, each one of these returns, remember, is a normal distribution, and it has a mean of h alpha and a variance of h sigma squared. And I add up n of them. Recall what n is. N is what defines h. H is equal to the period t over n. So I have n normal random variables, which I add up. They're all identically distributed. So the sum is normal, and moreover, I can determine the mean. The mean is n times h alpha, well, nh is t, and the variance is nh sigma squared, nh is t. So we see readily that the log ratio would appear to be normally distributed with a mean of alpha t and a variance of sigma squared alpha t, and we don't quite yet have that mysterious half sigma squared adjustment that we saw from Brownian motion earlier. So now the question becomes, where does that term come from? And the answer is, and we'll show it in a minute, the intuition is that it comes from the error term. The error term is a sum of squares in R, and I'll show just a little bit of the math as to how that sum of squares plausibly should give us the right answer.